An optocoupler is a component usually placed between two circuits, isolated from themselves, but communicate with themselves using light. It contains a light-emitting diode. Once we have current flowing in one of the circuits, the LED lights up and the phototransistor senses it and allows it to flow through the second circuit. This way, both circuits can remain isolated but communicate. They are widely used in power supplies for feedback control, isolating the high voltage parts from low voltage parts, but passing enough information to properly regulate the output voltage. Also, they can be used by DC circuits to switch AC loads, like the case of optotriacs and others. So let's look at parameters to consider before using an opto isolator. So here we have a datasheet from Sharp's PC817X series. Alright, if we go down to the second page, you will see we have the symbol for an optocoupler. Alright, we have the pin 1 and pin 2 connected to an LED, and we have 4 and 3 connected to a phototransistor. And we see pin 1 is an anode, 2 cathode for the LED, 3 and 4 pins for the emitter and collector of the transistor. Okay, so if we come way down, we'll see our absolute maximum ratings, and we have them divided into two sections: the input, the output, and we have other things. And for the input, we have the forward current. Now the input has to do with everything that has to do with our LED. Okay, so we have the forward current, which is 50 milliamps, and this means the current through the LED must be kept below this value as long as we want a good service life. Another thing to note is that the current level through the LED determines its brightness and would therefore affect how well the output responds to us. Alright, that's how well our transistors respond, because if the current we use will be too low, then our transistor will find it difficult to respond to the LED because the brightness will be affected. Okay, so we have the peak forward current, and that's the amount of current the LED can handle for a very short time, not continuously. So like for pulses, so if we have short pulses with low duty cycle, it can accept this current level. Okay, we have the reverse voltage. This is the maximum voltage our LED can accept in reverse without being damaged. So we can see that 6 volts. So we can't put anything above 6 volts on our LED in the opposite direction. All right, we have a power dissipation of 70 milliwatts. That's the amount of heat we can actually dispose during operation. So we have to confirm these values before we embark on any design. We have our output. So this talks about our phototransistor. We have the emitter collector voltage to be 6 volts. Okay, so the voltage between the emitter and the collector should not exceed 6 volts. All right, we have the collector current to be 50 milliamps, and that will mean on the output we can't put a load of above 50 milliamps on the output, otherwise we'll risk losing our optocoupler. All right, then we have the collector power dissipation to be 150 milliwatts, and that's the amount of heat, of course, the phototransistor can handle. All right, can actually dispose easily. Okay, so under here we have the total power dissipation. Of course, that's now the total power dissipation from the LED and the phototransistor, okay, together combined. And then we have our isolation voltage. This isolation voltage is the maximum voltage difference between the input side and the output side. That's the difference in voltage between the circuit on the input side and the circuit on the output side. All right, the difference should not be beyond 5 kilovolts. Okay, so that's the maximum we can have, 5 kilovolts. Otherwise we risk damaging the photocoupler too. Okay, then we have the operation temperature to be between -30 to 100 degrees, and then we have storage temperature, and we have our soldering temperature. Soldering temperature shouldn't exceed 260 degrees too. Of course, these are very important factors. Okay, so I'll make a simple demonstration of how this works with the Blink LED program from the Arduino. If you want to know how we got all that set up with the Arduino, you can click on the video on the screen. or you go to the description, you would see a link that will lead you straight to the video where you can see how we got the LED blink program done. Now if you look at the Arduino, our LED blinks every second, and on this side we have another circuit. If you look, you can see we have this red and black wire to be our power source. Okay, we'll be using a 9-volt battery. Okay, so the red is connected to the positive pin of the LED, and then the negative pin of the LED is connected to the collector of the phototransistor. Okay, and the emitter of the phototransistor is connected to a 330 ohms resistor down back to the ground of our power source. Okay, so this is a circuit, a different circuit on its own from the one we're going to be creating here. So we're going to have, of course, this is another circuit here. We'll be connecting the pin 13 of the Arduino that has this blinking signal. We'll connect it to the input of the optocoupler, which is the pin 1. Okay, so it will feed the LED. Now because we can't see that LED blink, I just dropped this other LED here, so we'll use it to see the blinking of the LED inside the optocoupler. All right, so whatever response this one is going to be giving us is what response the one inside will be giving within the optocoupler, and so we can see the reaction on this part of the circuit. Okay, and so we have it connected to a 1K resistor. So we connect pin 13 to our input. Okay, we can see our resistor is connected to the negative rail. Okay, so this line is all connected together, so we connect that line to our ground. And we see our LED blinks, and we see it blinks just together with the LED on the Arduino. Okay, so this is what's happening within the optocoupler or the opto isolator right now. The LED within it is blinking and sending signals to this part of the circuit to allow current flow through it. But we don't have a complete circuit here because we have nothing connected to our circuit. We have no power source. Okay, so let's connect our power source to it and see what response we get. So now we have our 9 volts power source connected, and we can see the response. Now both circuits are not connected together. We can see this is a circuit on its own, this is a circuit on its own, but this circuit has found a way to transfer information from here to this other circuit, and this is the basics for so many applications in electronics.